Hello, I'm Ben Arnack. I'm a professor here at the University of Cambridge, and these are going to be 24 50-minute lectures on symmetries, particles and fields. This is a course for master's students intending to learn the necessary techniques and tools of the trade to do a PhD in theoretical particle physics. So the idea is that during these lectures, you'll see my face, but I will also write on a tablet like I would on a blackboard, lecturing here at the university. All the mathematics is lectured this way at the University of Cambridge. That tends to slow us down, which is a good thing because we go fairly quickly anyway. But I would encourage you to take notes as I write. Many of us find that it helps assimilate the information. This process of taking notes somehow routes the information through the right bit of the brain and helps us assimilate it. But of course, everyone's different. Some people find, for example, that they need to talk about it with their peers and fellow students. And so, of course, you'll find whichever method works best for you, and you should follow that. So this course mirrors one that I give in part 3 of the Mathematical Tripos in Cambridge University. That is a master's level taught and examined course. And the courses are the same name. The course textbook will be this book here. This retails at £15. So it's the name of the course, Symmetries, Particles and Fields. It's by me, and you can just Google it and find it and buy it. It's got additional explanations and some additional detail to the calculations that we won't have time to cover here in lectures. It's also got exercises for you to work through when you get to them at the relevant point in the text. Without further ado, let's take some notes. Okay, so this is symmetries, particles and fields. The course is arranged into 10 chapters, just like the book, and this is chapter 1, the introduction. So we'll basically spend this first lecture on the introduction and the plan of the course. This is going to be quite hand-wavy, just because I'm giving you an overview of the kind of things we're going to cover and the sort of physics that it will be pertinent to. After this, we're going to get into proper mathematical detail and definitions and things. So let's start with the first word in the course title. That's a symmetry. What's a symmetry? Well, symmetry is a transformation that you can do on some system that leaves physical properties unchanged. So in terms of the particles and field theories that we're talking about, this might be energies, it might be scattering probabilities, etc. So a symmetry is a transformation, and we'll call these transformations in general G suffix I. So the I has a numerical value, and each different I gives you a different symmetry. So it's a transformation that leaves physical properties unchanged. Symmetries can be composed. We can do one after the other, for instance. So if I write G1, G2, what this means is we act first on the system with G2 and then with G1. The symmetries act towards the right. You'll notice that doing nothing is an action which we can describe as a transformation that leaves the physical properties unchanged. And so doing nothing is a symmetry. This sounds trivial, but it's more important than you'd think. We're going to call this particular symmetry not by one of the GIs, but by E, the identity it's called. So any symmetry transformation can be reversed. For example, a symmetry of an equilateral triangle is to rotate it in an anti-clockwise direction through 120 degrees. If I do that, you can't, and it's a perfect triangle, equilateral triangle, you can't tell whether I've done it or not. But I can always reverse that process and rotate it clockwise by 120 degrees as well, and that's also a symmetry. So a symmetry transformation GI can be reversed, and we call the reverse GI to the -1, which is itself a symmetry. Now, the set of all symmetries forms a group. The set that I'm talking about is the set of all symmetries that acts on our particular physical system that we're thinking about. So let's do a bit of recap about groups. Many of you will have seen some group theory, but some of you won't. So let's do a groups recap, a quick one. So a group, big G, is a set of elements These elements are going to be our symmetries, so G1, G2, etc., with 4 axioms. Firstly, there's a composition rule. So this is a binary operation. In other words, it acts on between 2 group elements. I'm going to call this here star here. So, and the binary operation must give you another operation, which is another member of the set, is in the group. So GI star GJ is in the group big G. So we shall often write GI star GJ as just GI/GJ. In other words, we'll often omit the star. So this means, for example, in the triangle case, you could rotate by 120 degrees and then do it again. That's another symmetry operation. The second axiom is that there must exist a unique identity element in the group, so little e, such that e times any member of the group or is equal to any member times e, acting on e, which is equal to just the group member. And that's for all elements of the group. Three, associativity. So I can compose 3 different symmetry operations, for instance. Let's call them GI, GJ, GK. Let's say they're all in the group. And the question is, even though I know I'm acting to the right, I've still got 2 orderings that I could do given these 3 compositions. I could do the composition of GI and GJ first, and then do the result of that with GK, or do the other case, which would be to compose the second 2 first. And associativity tells you it doesn't matter. which ones you do first. And so we can do either of these and we should get the same result. And so we omit the brackets. And this is for all GI, GJ, and GK in the group. Okay, so you may have seen some discrete finite groups. The finite refers to the number of elements in the set, the number of group elements. So let's give some examples of discrete finite groups. This first one is Zn. So this is defined by some integers, 0, 1, up to n-1. And the operation, the group operation, is addition mod n. So immediately we can look at this set of integers and tell which one is the identity element, because if we add 0 to any integer, it leaves the integer unchanged. So we can identify the identity there. The second example I'm going to give you is the cyclical group, Cn, and this is defined by some complex numbers. And these complex numbers will be 2 pi I r over n. So n is in the natural numbers including 0. So that's what this n0 means. So this is defined as 0, 1, 2, etc. Okay, so this colon equals is the way that I'm going to denote defined by. And R here is in the set 0 up to n-1. And the group operation is multiplication. So actually, these two groups are examples of groups where it doesn't matter which order you do the composition in. Some groups it does matter and some that it doesn't. If it doesn't matter, they're called abelian groups. So these are examples of abelian groups. Defined to be groups in which Gi, Gj is equal to Gj, Gi for all Gi, Gj in the group. Now you will notice that actually, I can define a one-to-one map between the cyclical group Cn and Zn. I just map, basically R tells us the map. So yeah. So in that case, if there is a bijective map between two groups, all the elements of the two groups, then they're said to be isomorphic. And that's the case here. So Zn and Cn are isomorphic. So there exists a bijective map between the elements that's consistent with the group composition rules. And we denote this as, well, we write one group, so Zn, and then we use this approximately equals symbol here. So if the group's on each side, that signifies isomorphism. So let's have another example. Let's look at the dihedral group D3. So you get various dihedral groups, Dn, and it's just the symmetries of a regular polygon with n sides in 2 dimensions. D3 is the symmetry group of an equilateral triangle. So let me draw an equilateral triangle. So as I mentioned before, I can rotate this, say anti-clockwise, by 2 pi by 3 radians. And unless I'd labeled the corners, you wouldn't be able to tell that I've done that. So that's the symmetry of the system. And I could rotate by 2 pi by 3, so that's a, or I could rotate by 4 pi by 3, that member is a squared, or I could do it all the way around by 2 pi, but then each triangle, each corner of the triangle ends up back where it started, and so that's the identity element. If I either rotate by 0 or by 2 pi. Okay, so there are some other operations, and there's various ways of phrasing these, but one way is to say we're allowed to reflect in this axis of symmetry vertically. So this reflection around this axis, it basically just swaps the bottom 2 corners of the triangle. So we end up with 6 different elements of the group. You have E, A squared, we have R, we can phrase it like RA and RA squared. Now there are other ways of phrasing it. You can use the other axes of symmetry or whatever, but the important thing is where the corners of the triangles, if you do label them, where they end up. And so there are 3 different corners, and there's 6 different possibilities for where they might end up after a transformation. And so the order of the group, the number of elements in the set is 6. And so whichever way you kind of describe it, there ought to be 6 elements. So what I can do is I can draw up a table of what happens if you compose one of the elements with another. I'm not going to do the whole thing. You can look in the book if you want to see, or look it up if you want to see the whole thing. So I can tell you immediately what the first line is, because this identity element E doesn't change anything. And we have A squared, E, RA squared, and R. A squared, E, A squared, R, and RA. So you can calculate the rest of this for yourself. And there's an exercise here, which is in the book, which just says, okay, try and do this for a square. So it's the dihedral group D4. You know, change the different symmetry operations that you would do in the case of a square, and write down the group composition table. So Lie groups are very important in particle physics. And they're a different case to these finite groups. Lie groups are about continuous symmetries, not discrete ones. They have continuous symmetries. So an example of this is a rotation of a circle around its center. By some angle. So the angle is the group parameter. And of course, that's the symmetry of the system. So this group, given by the rotations of a circle, we'll see later, this is SO2. That just means two-dimensional real rotations. So it turns out that Lie groups are essential for the description of particles. Well, it's describing particles and quantum field theories of them. Let me just say this, we're going to call this circle S1. S means sphere, and S1 is a one-dimensional sphere. Sphere means spherical surface in maths language. And so one-dimensional sphere is a circle. And I should point out that when we do this group composition, every element that we get by composing one set of the group by another, by the group axioms, has to be in the group. Okay, and that property that holds is called group closure. And of course, if we get an element of some that isn't in the group, then it's not, our description of the group is at least incomplete and maybe incorrect. Okay, so back to, now we know something about the fact that particle physics includes continuous symmetries in it. How are they used in particle physics, we can ask. And in fact, there's two different categories of symmetries. There's internal symmetries and external. So these are properties of the particles themselves. Okay, so they're actually properties of the fields as well. The way that we describe particles is in a relativistic quantum field theory. And so each particle species has a quantum field which is throughout space. And we have excitations, localized excitations in this quantum field. That's where we might measure a particle with some probability. Okay, so in some sense, particles, fields, and forces are synonymous because a force is the excitation of a quantum field in between two other particles, basically. So let's give an example of an internal symmetry. And I'm going to give the example of the color rotation of quarks. So let us take one species of quark, there's something called an up quark, for example. And each species comes with 3 otherwise identical copies, it turns out. And you can actually measure this. Basically, the chance of producing a quark is 3 times higher than you think it is, and it's because there are 3 copies of them. So we're going to just name these 3 copies by some label. We're going to call it color, so we'll call them red, green, and blue. So it turns out there is an exact symmetry in the standard model, which rotates the colors of quarks into other ones in a continuous manner, actually in a complex manner. So color rotation, rotation in this color space is a symmetry. And more than that, we can rotate, you know, all the red quarks everywhere into blue quarks if we wanted. But actually, it seems like the symmetry is much stronger than that. And if we insist that we can rotate red quarks into blue ones over here and red ones into green ones over here, and then change it tomorrow, that's what we call a local or a gauge symmetry. So in fact, in nature, this is the case. And it turns out when you try to build a quantum field theory that has this local symmetry property, you find you can't do it unless you add an additional force carrying field. In this case, the gluon. So the gluon carries a color and an anticolor. Okay, so it turns out that every continuous symmetry that you impose on the theory results in some conserved quantities. And this holds for external symmetries too. Every continuous symmetry leads to conserved quantities. There's actually a field theory proof of this called Nurse's theorem. Okay, and in this case, with the color symmetry, the conserved quantity is color. So it turns out quarks have a color; they're either red, green, or blue, or some mixture. Anti-quarks have an anti-color, so anti-red, anti-blue, anti-green, and the gluons, remember, have a color and anti-color. So what we can do is fuse a quark and an anti-quark to produce a gluon. So I'm going to draw you a Feynman diagram, which you won't understand yet, but it doesn't matter. You can get the heuristic picture. So what's happening is time is going in this direction. We're fusing an anti-quark. This is Q bar. Let's say that's anti-blue. And we'll fuse that with some quark. Let's say that's red. Got red color, and then we produce this squiggly line. This represents a gluon, and this would have a color red anti-blue, and it would have that color such that the initial color state, which is red anti-blue, remains conserved. And it's actually the group structure, the mathematical group structure of the theory tells you that color is conserved. So in the case that the symmetry doesn't, you can't do different symmetry transformations at different space and time, it has to be the same everywhere, it's called a global symmetry. It's a global symmetry. Okay, so external symmetries aren't just to do with the particles themselves, they actually involve the space-time coordinates directly. So these are symmetries which act directly on the space-time coordinates. So, for example, spatial rotations, a Lorentz transformation or Lorentz boost, and translations in space or time. And so the conserved quantities that come along with these symmetries, well, the translation in time gives you a conservation of energy. Translation in space, symmetry gives you conservation of momentum. Rotational symmetry gives you conservation of angular momentum, etc. So up until now, the symmetries I've been talking about are exact as far as we know. I mean, they've been probed and we haven't found any chinks in their armor. But there are cases where they're only approximate, but you can still use them to infer some facts about, to explain some mysteries about the universe. And we'll see that in chapter 7, where we use an approximate symmetry to explain the spectrum of hadronic particles, which is seen. But speaking of particles, let's talk of fundamental particles. As far as we know, these are fundamental. So I'm only going to tell you about particles which have definitely been observed. And we're going to start with particles or quantum fields that carry force to begin with. Force carriers. So we have the gluon, which we've just met. G, gluon. Oops. So we'll write the name, the spin in units of h bar, the mass, and which force it is. So the gluon is a spin 1, it's massless, and it carries the nuclear strong force. So this fixes this glue. It's called the gluon because it glues quarks together in a proton, for instance, and it's a strong force. Gamma is the photon. This carries electromagnetism. It's got spin 1 and its mass is 0. And we know about W and Z bosons. So these were discovered at CERN. W boson and the Z boson. These are also spin 1, but these have a mass, and they're roughly 100 times the mass of the proton. And so these are the force carriers of the electroweak force. So these are responsible, for example, for radioactive decay of nuclei. And there is this other hypothetical particle, which I'm putting an asterisk on, because this one hasn't been discovered. But there are good theoretical reasons for believing in it. This is the graviton. Of course, it carries the gravitational force. It would be, if the theory is right, it would be massless, and the spin would be 2. So the massless force carriers, these come from unbroken gauge symmetries. We'll define gauge symmetries in generality, quantum field theories of gauge symmetries, in section 8, chapter 8. But the massive ones, like these electroweak gauge bosons, they come from a symmetry which in the overall theory is exact, but it's spontaneously broken. So it means that the vacuum, somehow the vacuum state breaks that symmetry. That breaking is actually the Higgs mechanism. It gives mass to the fundamental particles, including to the force carriers. Okay, so those are the force carriers. Let's look now at the matter particles. So these are spin 1/2, h bar, and we have up quarks. So their charge in units of the electron charge, I guess in units of the positron charge is +2/3, and the number of colors of an up quark is 3. And we have a down quark. Charge is -1/3. Again, it's got 3 colors. We have this nu, which is the neutrino. This is electric chargeless, and it has there isn't any color state. It's just, it doesn't have color copies. And the electron has a charge of -1 in these units, no color state. So in a quantum field theory, each one of these matter particles comes with an anti-particle copy. Lorentz symmetry and locality of the quantum field theory tell you that the mass of the antiparticle has to be the same. It feels the effective forces in the same way, well, with the same strength, I should say. But the electric charge is opposite. So opposite sign, charge, and an anti-color. If they have the colors, then the antiparticles have anticolors. Now, actually, matter particles come in 3 families, and what I've just described to you is just one family. So of each of these, we've got 3 copies of them, each successively heavier, each with their own antiparticle copies and so on. So all of these particles which I've just told you about, which as far as we know are fundamental, these fit into the standard model of particle physics. Each one has a quantum field associated with it. So standard model, very successful theory of particles. So standard model is a quantum field theory with a Lie group structure. Good. So what I want to do now is just finish with a rough sketch of the plan of the rest of the course. So section 1, which we're halfway through, is just going to be some more basic definitions about groups and subgroups and so on. And that should only take us about a lecture. Chapter 2. So these are going to be about Lie groups. So we're going to define Lie groups mathematically. It turns out that there's an algebra, a Lie algebra it's called, that you can also describe the groups by. We call this L of G, Lie algebra. There's a map from a Lie algebra to a Lie group. It's an exponential map. It's often simpler to work with the Lie algebra, which is why we'll focus on them. But we'll also describe here matrix groups. So yeah, some of the Lie groups, well, the Lie groups are matrix groups, basically. So section 3. So it turns out that we can represent both Lie groups and Lie algebras with matrices, non-singular square matrices, and we can represent the group operation with matrix multiplication. And these matrices to represent each group are called representations for obvious reasons. So if we have some n times n matrix, which represents a group, that's actually going to be represent the rotation, for example, in this color space. So in that case, it would be a 3 by 3 kind of complex rotational matrix that acts on a space, a vector space, which is actually the color space. So that would be the red, green, and blue colors of one of the quarks, for instance. Okay, section 4, we're going to look at the simplest Lie algebras and groups. And the simplest sort of non-trivial ones. And they're SO3 and SU2. And these have physical relevance. They describe angular momentum states. SU2 describes angular momentum states in quantum theory as well. And actually, analyzing representations in terms of these will allow us to do the more general case for more general groups. Then we'll go on to do relativistic symmetries. So we have two relativistic symmetries that are relevant. Lorentz symmetry. This is a Lie group. So rotations and Lorentz boosts. And Poincare symmetry, which is when you take Lorentz symmetries and you add translations in time and space. So you're saying the laws of physics shouldn't depend on when you do your experiment or where you do it. And Lorentz symmetry tells you it shouldn't depend upon, you know, the angle of your experiment, for instance. Okay, so then chapter 6, we are going to look at roots and weights. So these are objects in a way of mapping the group algebra, the Lie algebra, into a geometric picture. You get some vectors in a certain space, and they're the roots and weights. So this is a geometrical picture, and this is the key to unlocking results in general Lie groups, and it's how we describe representations, for example, and the group itself. Okay, section 7, hadronic physics. This is the case where we can place known hadronic particles using this approximate symmetry that there exists actually between 3 different types of quark. So this is a nice application of some of the group theory that we've developed in the previous chapter. Then we'll look at field theories for this gauge theory case, where you make sure that you can do different transformations at different space-time points, and it should still be a symmetry of the theory. So the standard model is built really on gauge theory. So these are essential for understanding that. And finally, we'll just return to representations of the Poincare group. So it turns out that one particle states are unitary, infinitely dimensional representations of the Poincare group. It's a tricky topic that we need some of the previous results for just at the end of the course. But this is going to describe for you, for example, why physical photons have no spin 0 state. Remember, they're spin 1, and usually with spin 1 quantum states, you can have either +1, -1, or 0. But for massless particles, something else happens, and you miss out the 0 state. So we'll describe that in the 9th chapter. 10th chapter is just this short thing called an epilogue. So here I'm just going to sketch for you in much the way that I've been sketching here just now, some of the topics which we haven't covered, which we could well have done were we to extend the course in several directions. So thanks for listening to the first lecture. Next week, in the next lecture, we shall start with basic group definitions and just a few bits of group machinery that we'll need.